In this section we talk about extreme values, and by extreme values we mean maximum and minimum values of the function. Maximum is two types: relative max, or sometimes called local max, and absolute max. And minimum is relative minimum or local minimum and absolute minimum. Now, what do we mean by each one of these words? What do we mean by relative max, relative min, absolute max, absolute min? So if we take a look at this function f of x, this is a graph of function f of x defined from a to b. And let's denote these values here, this as x1, this is x2, this is x3, this is x4. Now if we look at this graph, we find that f of x1, this point here, is maximum. This is maximum, and the derivative, the slope of the tangent line derivative at x1 is equal to 0 because the tangent line is horizontal. And here at x2, the slope of the tangent line is equal to 0 because the tangent line is horizontal, so the derivative at x2 equals 0. And here at x3, the derivative at x3 equals 0. At x4, derivative does not exist or undefined. Here, derivative f prime of x4 is undefined. Undefined because we know that derivatives are not defined at sharp edges, and this is a sharp edge. Now what about the endpoints? The endpoints of the closed interval, at these points, at the endpoints, the derivative does not exist because the derivative is defined to the right of this point, but it's not. We don't know anything about the derivative to the left of the point A. Similarly, we don't know anything about the derivative to the right of B, but we know the derivative to the left of B. And the derivative, in order for the derivative to be exist, the derivative should be existed from left and from right. So here the derivative exists from one side. That means the derivative does not exist at the endpoint. So this is endpoint and this is another endpoint. Okay. Now if we look at the function, we find that the function is increasing just before x1, the image of x1, and it's decreasing after that. So the function here is increasing. That means any slope will be positive here. So f prime of x is greater than 0 here. We use different color. So here f prime of x is greater than 0, positive, and here f prime of x is less than 0 because it's decreasing. The function is decreasing. Similarly here, the derivative is greater than 0. Here the derivative is less than 0, and so on. So what does that mean? That means if we have a point with derivative equal to 0 or derivative undefined derivative, then we have a maximum or minimum. For example, here we have a maximum. This is maximum. This point here is minimum. This point is maximum. This point is minimum. This point is max, and this point is minimum. So now how can we determine if the point is relative max or absolute max, relative min or absolute min? This is our question here, how to determine whether it's if the point is relative max, how to determine if a point is relative max or min, or relative or absolute max or min. This is another question. Now let's back to this description here. So at x1, f of x1, or the function, has a maximum point at x1 and f of x1. So at x1 we have a maximum point, and if we look at the derivatives, the derivative is positive to the left of this point, and it's positive to the right of this point. So the function is increasing to the left of the x1 and decreasing to the right of x1. That means we have a maximum point. This is relative max. Relative maximum. Now, if we look at the point x2, look at the derivative. The derivative is negative to the left and positive to the right. That means it's decreasing from the left and increasing from the right of x2, and this means that this point is relative minimum. Now all points, whether they are relative max, relative min, or absolute max, absolute min, we can call them relative extrema. So every point of these is relative, but not every one of them is absolute. Now how to determine whether it's absolute or relative? Look at the point x1. For point x1, we notice that this point is maximum, but this is not the highest point or the largest value of the whole values in the domain, for the whole domain. Because if we look at B is maximum. B and f of B is a maximum point, and it's larger than x1 and f of x1. So this is larger than this. So one of them should be absolute max. As you can see, this one, the maximum at B, is the absolute max point because it's the highest point of the whole graph on the domain. And x1 and f of x1 is a maximum, but it's not the highest point or the largest value. So f of x1 is not largest value, means that it's local max. We also have another local max at x3. This is a local max at x3 because it's maximum, but it's not the largest. F of x3 is not the largest value of the function. So that's what we mean by relative max and absolute max. So the highest value is absolute max. The other max are relative max. I mean by relative, it's the maximum on some interval here around x3. So it's maximum over this interval, but it's not the maximum or the largest value over the whole domain. Similarly, at x1, this is the largest value over some interval here over this interval, but it's not the highest value over the whole domain. Same thing is correct for the minimum values. For example, f of x2 is minimum, but it's relative minimum because we have smaller value, which is a and f of a. This is smaller, so this is absolute minimum. Now we can summarize this here. So we say that f has relative minimum at x equals x naught if the values of the function are greater than or equal the value of the function at this point. I mean, everything is larger than this or equal to this point on some open interval for every x in some open interval around x naught, and its relative max at x equals x naught if f of x is less than or equal to f of x naught. That means all values of the function are less than the value of the function at that specific point, less than or equal to that value. So that means it's larger than any value else or equal, but where on some interval for every x in some open interval around x naught, but not over the whole domain. This is the relative max, relative min, and f has absolute minimum if at x equals x naught if this is true, f of x is greater than or equal f of x naught for x and for any x in the domain, for every x in the domain. I mean on the whole domain of the function. And maximum, absolute maximum at x equals x naught if f of x is less than or equal to f of x naught for every x in the domain of the function, not only on some interval, open interval, but on the whole domain. So that's what the difference between absolute and relative max and relative absolute min. Now we have, if we look again at the graph, we notice that the function has maximum or minimum, relative max or absolute max, relative min or absolute min at some points with some property. The property is that the derivative is either equal to 0 at these points or derivative is undefined. So that's what we mean by critical point. So a point x equals x naught is a critical point f of the function f of x if one of two things happens. F prime, the derivative at this x naught equal to 0, if the derivative is 0, as we've seen here, for example for x1 or x3 or x2, or the derivative is undefined, evaluated at x naught. The derivative evaluated at x naught is undefined. For example, the derivative does not exist or undefined at x equals 4 because this is a sharp edge. Okay, so when the derivative at specific point equals 0, we call the point, the critical point, stationary critical point. And if the derivative is undefined, then the point is singular critical point. Okay, now let's take some examples on how to find the critical point and intervals of increase and intervals of decrease. So if f of x is x squared plus minus 2x defined on the interval 0, 4, we want to find all critical points. We denote critical points as CP. So to answer this, we find the derivative of the function. The derivative is 2x minus 2. Now we have two things to think about. Alpha prime of x equal to 0. That means 2x minus 2 equals 0. And this gives 2x equals 2. That means x equals 1. This is a critical point. Or alpha prime of x is undefined, but this is impossible for this function. Alpha prime is defined for any value. So we only have one critical point. Now let's take another example. Now if f of x equals 3x to the power 5/3 minus 15x to 2/3, we want to find all critical points. Let's find all critical points first. So we find the derivative. What is the derivative of this? It's 3 times 5/3 x to 5/3 minus 1, applying the power rule, minus 15 times 2/3 x to 2/3 minus 1. Then we can simplify more. 5x to the power 2/3 minus 5 times 2, 10x to the power negative 1/3. We can write this as 5x to 2/3 minus 10 over cube root of x, because this is x to negative 1/3. When we bring it down, it becomes x to 1/3. If we don't want to use the radical or the cube root, we just write it as x to the power positive 1/3. Now this is the derivative of the function. So this function, this derivative is equal to 0, or derivative is undefined. This way we can determine the critical points. Let's start with the first case. If alpha prime of x equals 0, then 5x to 2/3 minus 10 over x to 1/3 equal to 0. And then we can bring this to the right hand side. We get 5x to 2/3 equals 10 over 10 to 1/3. Now let's multiply both sides by x to 1/3 to get rid of this denominator. So we have 5 times x. Now we add the powers. 2/3 plus 1/3, 3/3, which equals to 1, which is equal to 1. This is equal to 10, and then we divide by 5. X equals 2. So this is a critical point. Let's try to find another critical point. Now the other critical point can be obtained by checking if alpha prime of x is undefined. If we look at the function, this is undefined. If it's undefined if x equals 0, because this is alpha prime. When x equals 0, this function is undefined. That means we have 0 in the denominator. So we have that x equals 0 is a critical point. Okay, so these are the 2 points that we are interested in. Now we can determine the intervals where the function is increasing, intervals where the function is decreasing. Let's determine this here. Now part B, we want to find intervals where the function f of x is increasing or decreasing. Now, how to find this? Let me first define what we mean by increasing and decreasing function, or how to find these intervals. So we say that f is increasing on some interval if the derivative is greater than 0 on that interval, if the derivative is positive. The function is decreasing on some interval if the derivative is less than 0. The function is constant on some interval if the derivative is equal to 0. So this is how we determine these intervals. Now let's do this for our problem. So we first determine, we study the sign of f prime, its sign chart for f prime, and we put the critical points on this line. The critical points are 0 and 2. 0 and 2. Now, since critical points are 0 and 2, we can study the sign of f prime. F prime is this function. So let's choose a value that's greater than 2. We can choose 3 here, and a value between 0 and 2, let's choose 1. A value less than 0, let's choose -1. When we choose 3, let's substitute it into f prime. We don't need to determine the value exactly, but we need to know at least the sign. So if we substitute 3, 5 times 3 to 2/3 minus 10 over cube root of 3. So this is 5 times, now 3 to the power 2/3 is 9 cube root of 9 minus 10 over cube root of 3. Now, is this positive or negative? Now, using calculator, we find that this is positive. Now, let's choose a value between 0 and 2. If we choose a value between 0 and 2, we substitute it into f prime. We get 5 times 1 to 2/3 minus 10 over 1 to 1/3. This is 5 minus 10. It's negative, less than 0. So the sign here is negative. Let's choose a value less than 0. We choose -1. So if this is -1, then we get 5 minus 10, and that's positive. It's greater than 0. So this is positive. That means the function is increasing here, decreasing here, and increasing here. So f is increasing on the interval negative infinity to 0, and from 2 to infinity, and f is decreasing on the interval 0 2, as we can see here. Now let's determine the extreme values by using the same sign chart of f prime. We find that the function has a maximum at 0, relative max at 0, and relative min at 2. So this is relative max, this is relative min. So the function has relative max at x equals 0, and that point is 0 off of 0. And the other point, the function has relative minimum at x equals 2, and that is 2 and f of 2. Now f of 0 is 0, so this point is 0, 0, and the other point f of 2 is, now we need to substitute here f of 2, so let's do it here. 3 times 2 to 5/3 minus 15 times 2 to 2/3. Now we find it's 32 cube root of 32 minus 15 cube root of 4. So we can leave it in this form, or we can use a calculator for that. So it's 2 and f of 2. I'll leave it in this form. You can use the calculator to find this value. So that's how we find the relative max, relative min. Here, since we don't have the interval is not bounded, it's the function is defined from negative infinity to infinity, not from, for example, -1 to 3. If it's defined on some specific interval, it becomes easier to find absolute values. But in this case, we don't know exactly what is the absolute max, because it's still increasing here, and it's still increasing from here. That means the function has relative max and relative min. Let's take another example. Let f of x equals x squared minus 2x on the interval 0, 4. We want to find the extreme values. Find the extreme values of this function. So to find the extreme values, we have some steps. First, we find f prime, the derivative, and then the critical points. Let's find f prime and the critical points. F prime of x equals 2x minus 2. Critical points, we set this equal to 0. And that means 2x minus 2 equals 0. We did this before. It's x equals 1. This is the critical point. This is called stationary critical point. The second step is to make a sign chart of f prime of x. So we have f prime here, and the critical point is 1. This is a critical point, and then we study the sign of f prime. If we choose a value that's greater than 1, like 2, and a value less than 1, like 0, substitute them into f prime. This is f prime. When we substitute 2, we get positive value. When we substitute 0, we get negative value. So the function is decreasing here and increasing here. That means this point, x equals 1, the function f has a minimum point at x equals 1. But we have interval here. As you can see, it's defined on the interval 0, 4, so we need to include it from 0 to 4. So in order to determine which one is it relative or absolute, we need to determine the endpoints as well. This is endpoint, and this is another endpoint, and we have critical point, stationary critical point. So we have the following points. We have 0 and f of 0, and we have 1 and f of 1. We have 4 and f of 4. So 0 and f of 0, as you can see, this is maximum because the function is decreasing from here. So it's maximum, but it's relative max, because if we find the value of the function at these points, this is 0 and f of 0. F of 0 is 0. This is 1 and f of 1. F of 1 is -1. And this is 4 and f of 4. alpha 4 is 8. So this is max. At 0 it's maximum, and at 4 it's maximum. As we can see here, it's maximum. But this is absolute max because it's the largest value on the interval, and this is relative max. The other one is just relative max. And what about 1, -1? 1, -1 is relative. It's absolute min. It's the smallest value here in this interval, so it's absolute minimum. And this is how we determine these points: the relative max, relative min, absolute max, absolute min. Now we have some useful theorem. If the function f of x is continuous on some interval ab, then there exists a maximum and a minimum on that interval. Because if the function is continuous on some interval, for example, this is continuous on some interval a to b, so we should have minimum value and maximum value of that function. But if the function is not continuous, for example, if the function looks like this is a removable discontinuity. The function is not continuous at the point c, so that means we don't have maximum, no max. If the function looks like this, the function doesn't have minimum, no minimum, because it's not continuous at a. Now let's do another example. So let's do this example. F of x is x cubed minus 3x squared plus 5. We want to find all extrema. Extrema means extreme values. So in this case we find the derivative. So the derivative is 3x squared minus 6x, and then we set this equal to 0, alpha prime of x equal to 0, and that means 3x squared minus 6x equal to 0. We take 3x as a common factor. We are left with x minus 2 equal to 0. So we have 3x equals 0, that means x equal to 0, and x minus 2 equals 0, that means x equal to 2. Those are stationary critical points, this and this. We don't have singular critical points because the function is defined. Second, defined everywhere. So second, we find we draw or make a sign chart of alpha prime of x to determine the interval of increase, intervals of decrease. So this is alpha prime. We put the critical points here and we study the sign. Let's choose some values here, some value less than 2, greater than 2, like 3, between 0 and 2, 1, and less than 0, let's use -1, and substitute into alpha prime. So alpha prime is this function, or we can use this form of the function because those are equivalent and it's easier to find the sign from this. Now if we substitute 3 here, it's 3 times 3 positive, and substitute 3 here, 3 times minus 2 is positive. Positive times positive is positive. Now between 0 and 2, let's choose 1. If we substitute 1 here, 3 times 1 is positive. If we substitute 1 here in x minus 2, we have negative. So positive times negative is negative. Now let's substitute -1 in 3x times x minus 2, which is equivalent to our original function, or original derivative function, 3x squared minus 6x. So as I mentioned, it's easier to substitute here to determine the sign than using the original derivative. So substitute -1, 3 times -1 is negative, -1 minus 2 is -3, negative times negative is positive. So it's positive here. It's increasing, decreasing, increasing, and that means we don't have interval. So the function has relative max here at 0 and relative minimum at x equals 2. So relative max at x equals 0, and that point is 0, and f of 0 we substitute into the original function. F of 0 is 5, so it's 0, 5. At 0, 5 we have relative max, and relative min at x equals 2, so we have 2 and f of 2, 2, and we substitute 2 into the original function. This is 8 minus 12 plus 5. This is equal to 1. So at 2, 1 we have a relative min. Now we have another useful theorem or result that says if the function f of x is continuous on some interval a, b, and f of c is minimum or maximum on a, b, then c is a critical point or end point. So that means this theorem tells us where to find the extreme values. Tells us where to find extreme values. We find them on at the critical points. They are either critical points or endpoints of the interval. If we want to determine intervals where the function is increasing, now here we can add it here. So f is increasing on negative infinity to 0 union 2 to infinity, and f is decreasing on the interval 0 to 2.